Chapelle in 2000 before. And then I came to several talks, meetings, and last year I came to Forest Park, here I'm again. Indeed, I am an engineer, and I think the final habitat should be experiment, not math, not sorry to build. But of course, I agree that logical thinking should rule in the derivation of whatever the theory is. I have changed my talk. I was planning to talk before only about my experimental part, the nitrogen Morley type, which is basically based on shadows. We see a lot of fringes, different shadows, and I was going to talk about all the nuances that are there in the interpretation of those shadows that we see and we interpret as something physical. With some physical meaning that are in the context of a particular model that we have in our mind. So, but I decided then to talk more about the overall idea of what a unified theory, I used to say model, but as people here prefer theory, when you have a set of postulates, I would say theory of nature. So that's what I'm going to talk. And I want to start with a look back before. I am a classical physicist. I would like to go back and wind up the clock 120 years back before Einstein and quantum mechanics. Whether we can derive from there a workable theory. Of course, we need then to go back and predict everything that has been obtained during the last 20 years, of course, clear. But I want to talk about that. Please bear with me and come back to the time of Hertz on Periside. That was 1890s, when I think physics derailed and became something ruled by more by thinking than by experiments themselves. Okay. So now I forgot how to do it.
That's the computer.
Oh, sorry. So, basically, we measure in nature, and there is an interaction between us and the material we are measuring. In my view, the special theory of relativity and quantum mechanics overstressed the importance of the observer, and they became theories of how a particular being observes nature rather than how nature behaves when we are not bothering her. And in my view, this should be the goal to understand nature. This is important, of course, but this is the goal. So, again. So, I am very glad that Charles is here. And in my view, the most fundamental force is not of electromagnetic origin. I think the most fundamental force is mechanics. It's a mechanical origin. Of course, electromagnetism is just a cause, and it's an effect of the behavior of mechanical particles in the famous ether, infamous, I would say, rather than famous, the poor ether. So that is, I'm going to go back, as I said, to the 15th century, and I start from the ether that Hertz has had in his mind when he passed away. Unfortunately, he passed away when he was 30-something, 37 or something like that, and left a big hole in science, a very big hole that we didn't have anyone to fill until Einstein came. So, I don't want to start with Newton. I will go a little bit backwards. And the three laws of Newton can be derived from a single principle, which is conservation of linear momentum, which is a Cartesian idea, a Huygens idea, and I will go back to those. And in my view, this is classical physics. These are the linear momentum has not been violated up to now, except in some of the theories where they have left out the so-called field. Otherwise, linear momentum has never been violated conservation. And the other important property of matter and photons is that they occupy a place in the space we live here. And we are matter and we occupy space. And there is no particular reason why when you go back, down, it has to change. So the idealization that Newton had, that there are point particles with matter, is not here in this model. I think the smallest particle should still have the same properties that the largest particle has, and that is station. So when we introduce that one immediately gets into the realm of quantum mechanics from classical theory. So the reason we didn't get quantum mechanics before is because we assumed that it was okay for Newton. That was a very important mathematical theory we had about center of mass. But it was okay at that time, but it was not at the later time. So when we introduce extension as part of the theory, then quantum mechanics comes naturally. I think I will go with it. Okay. Any physical theory on these assumptions, most of the time implicit. Okay. And the assumptions may be classified into groups which will go very quickly over them. Logical and epistemological principles, and some rules that we have in our mind to guide us. Metaphysical assumptions or postulates regarding nature herself, and some physical postulates usually based on empirical experience. I say usually because some of the postulates that Einstein postulated, the empirical basis is very shaky. I think Greg will have something to say about Lorentzian interpretation of the Michael-Moore experiment. I have my interpretation, you do the same, but they are not. So, this is my group of assumptions. So,
this one here.
I have one here. Comprehensibility of nature. It's possible to understand nature. I think we can do it at least partially. Is the human race the center of the universe? Well, you remember Aristotle. The earth was the center of the universe in the time of Aristotle. And in the time of 20th century physics, now the man is the center of the universe. You are now the anthropic principle. No, the man is not the center of the universe. Tomorrow, the earth may be destroyed, and the rest of the world will stay there. I mean, galaxies and everything will stay there if we are destroyed tomorrow, the whole earth. That's my view. If you have somebody may have another. Okay. The question about how to formulate general principles, that requires some inference or empirical data, that interpretation of data, which is a very, very tricky thing, and some informed guessing and extrapolation. If you remember, for instance, Galileo, when he discovered the principle of inertia, he did that with some balls rolling and things like those, and then he extrapolated from there to how a punctual or a small particle will behave in the vacuum, away from the friction that you made the experiments in. So there is always a need to extrapolate if you want to get to general principle. So that is something that you may require adjustment, and this is what we are usually doing when we change our way of thinking as we progress in the search of a theory. Other things important are for theory should be falsifiable. That's the idea of Moscovich and identified Popper.
Of course, Occam's razor. One simple principles are preferable. This is why I go to Cartesian ideas and Euclidean ideas rather than Newton, because with only one principle you get three laws. This is why I prefer that. And in my view, mental objects are very important, of course. Equations, the principle, the principle of probability, our models of nature, they are very important, but they are not nature. They are just something that we use to understand nature, but they are not nature by any means. Physical objects exist independently of humans, as I already said, and I believe in causality. Causality should antecede, should precede in time the effect. The cause should be before the effect. That's clear for me. And interaction at a distance? No. That puts stringent limitations to the way we think. We are not going to say, well, gravity is there and it's magic. No, it's not. We should try to find a mechanism for those processes, to understand those processes. Okay? And this is Leibniz's principle. Continuity in natural processes. Are there instantaneous changes in nature? No. Why? Because to go from one state to another state, you should pass through the intermediate states in between. So to go from speed 100 kilometers per hour to speed 0, you have to go to 99, 98, blah, 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 down to 0. So that is Leibniz's principle of continuity, and if one adopts this, of course quantum mechanics in the sense of jumps is not allowed, but it is allowed a very quick change. That's something else, completely different. And this has a very important consequence. When you apply this to your physical processes, you find something very interesting immediately. Any physical processes involved in different states requires a finite time. And it requires a finite time that should be the smallest time for the shortest process. And that smallest time in nature should be tau, say. And this has an implication for the idea of derivative as we know it. Of course, we cannot blame Newton. I don't blame Newton at all. He did a lot. He invented this, or Leibniz, whatever it was. Because I don't care whether it was Leibniz or Newton myself. I'm not pragmatic. So, whoever it was, Newton or Leibniz, they invented this, wonderful. But then, now we know better, and we think, okay, if there is a small tau, this is our definition, and this is now an average, and it has a limit. So we can go using this, but with the understanding that there is a limiting process in there. A limiting process where this is down to tau, and so this is an average actually. This idea, you check Russell's principles of mathematics, he is concerned with this also. He has about 100 pages discussing in his book, The Principles of Mathematics, those ideas about how velocity and acceleration are not properties of a point in space, but are rather average processes. So this is very important. So this is extremely important. And the companion to this, I will jump to something I will say later on. I already said that if matter occupies a portion of 3D space, then the smallest piece of the space, the smallest length, should be associated with the smallest bit of matter, and that would be, say, lambda, that's the smallest length, and then also the companion, the spatial derivative would be something like this, where these R stand for X, Y, and Z, and then you have the standard one, and then you have the new one. You can go on using this, but with understanding that there is a limitation here. The limitation. And these limitations, the one on time and the one on space, immediately lead to vice versa principle. I am not going to deny that, but this is fairly obvious that if motion is the primitive concept which I am adopting from Cartesian view, mass is not a primitive concept in Cartesian view, but the amount, the quantity of motion, the product of M and V, is the basic concept. Then, in that case, in that sense, D is a limited. The smallest one will be something like this, and is quantized in that sense, and Heisenberg's uncertainty will come out of that. That idea we got a long time ago. This is a sense in the early 90s. So, what are my metaphysical assumptions? All theories have metaphysical assumptions. Einstein said there is a space-time. Okay, that's good for him. I don't say that. I say there is physical 3D space, this space, and I don't agree with that to Newton. It's the same, very similar to Newton, but I agree with that to Patrici, who 100 years before Newton's Principia, he published that. It's not translated into English, it was in Latin, of course. It's not translated into English, you can find that in the literature. Brinkman, I think, translated it. So it's very similar to Newton's physical space, but this is Patrici's physical space. Of course, Newton's physical time, and Planck spotted that they did not exist at the time. I mean, they existed, but they were not aware of them. That's something else. They did exist photons, of course, all the time have existed. Light has existed even in the Bible. Then there will be light. But this is not the question. The question is that photons were discovered by Planck in the 1900s, and this is an object that is neither space nor matter, because this object only exists in motion, whereas matter doesn't exist and rest in our space. So it cannot be matter. It has to be something else, and that something else is energy. It's one of the building pillars of modern physics, including Einstein's, of course, special relativity and general relativity in the question they have. And so, matter is associated with motion in physical space, and in our model, I mean, Cartesian model, it is, the primitive notion is quantity of motion. So there are very interesting results from there, and there are some 2 or 3 books that have developed classical mechanics from those ideas. One in Karlsruhe, Professor Hermann and Professor Berloch in Florida. They wrote the books of classical mechanics based on Cartesian ideas. So Patrician space, I will go quickly over this. You have he says that there are 2 regions in space. In that overall space, one, the part is occupied by us here, bounded by the surfaces of the objects we have here. We can change form in shape in this region, and there is the region beyond this universe, and so we are at the boundary of the universe, and we stretch our arm out, we still are in the same space. So no problem, no contradiction there in the view of Patrici. So this is very nice. And the advantage of this particular region of the universe is that empty space in this region, in our region, can be easily measured in 2 dimensions. If you expand that object into this shape and you take a part out, you have empty space here, and this empty space now has the properties of 3D. Because you can measure that when it is bounded by our matter. Of course, that's clear. So you can assign to empty space also 3D. That's clear, and that is in Patricius. Of course, we didn't show this example, but it's in Patricius. Newton, of course, everybody knows here our Newton, so I don't have to read this. This is what he says in the Principia, very clear. And that's classical mechanism, and we know it. But what is important is the difference between what absolute time is and what is measured time, that Newton stressed. So if we take the old method in the time of Newton and the time of the Egyptians, a sun clock, say, and we have the sun clock and different positions in the earth, one possibility is to have it the equator, and you have there some zero that will pull, in the sense of Newton, pull the sun down, so will measure some time. And we take that to the pole, we have a different G, so this will not measure the same thing. Or do you have to take that to the top of the Everest or to the top of the Concagua in South America? That will measure something different because very high, some G is different. But it doesn't mean, of course, that time is different. What is different is the measurement of time, which is another matter. The time is still there, but you are measuring it differently. That is the big difference. That has to be with special general relativity and the meaning of those experiments of Einstein. I wanted to talk about that before, but I will go on another time with that matter. I don't have time to do that. But you can really find the simultaneity in special relativity in a different way. So I'm taking a different one. I have done that consciously, a different one to Einstein's method, just to avoid discussion for the time being. But I can go on that on another occasion. So, photons. Photons, this is the electromagnetic spectrum. We know all of us, especially engineers and physicists, of course. We go from very low energy associated with power cables up to high energy X-rays. Actually, these are the highest than the gamma rays. The gamma rays are associated with nuclear processes. X-rays in the large machines, then they come up to this point. The cosmic rays are not electromagnetic. They produce gamma rays and X-rays, but they are material rays. These are not really cosmic rays. They are not really electromagnetic. Okay. So the duality is well known from Einstein and de Broglie, and this is the usual thing. Sometimes in waves, sometimes in matter. I have something to say there. Let's clarify that. I am an engineer, let's go back to the sea, to the good old sea. Dirac also thought of his ether as a sea. But let's go to the sea, to the real sea. So, a water molecule, there are in 18 grams of water, there are Avogadro number of molecules. It's well known, we can high school numbers. So, obviously, water molecule is matter, clear. And what are the waves? Well, the waves are the collective behavior of many tons of water. See, you have a small pond, 1 kilometer by 1 kilometer by 100 meters by 30 meters, that contains 10 to the 35 molecules. So this is 18 grams, this is some tons. So the collective motion of all that matter behaves as waves. But waves are not something different from matter. They are just the behavior of a lot of molecules of matter. That's all. So there is no duality in that sense. The wave matter duality. Where it is, no matter. I mean, that is the Broglie's idea that the electron is blah, blah, blah. But this is, in macroscopic way, there is no duality matter. What there is the duality you want to say, or whatever, between one particle and many particles, and the same with the photon. You have the photon, which have pieces of energy as discovered by Planck and Einstein in his interpretation of the electromagnetic of the photoelectric process. Then photons, and they are traveling. And what we have is collective behavior of many millions of photons is what produces the wave behavior of photons. Photons may have a structure. That's an idea I posed in BCM 2000. I described there the photon as charged dipoles, and then this idea was elaborated in another paper I published in Wiley, what they then said that about 200 in Eva's book, on longitudinal solutions of Maxwell equations. Okay, so this is an alternative view of what is going on. This is not that the wave is something different, but rather a property of many. So, in that context, I want to postulate that the ether is no longer a set of small balls of matter, but rather a lot of photons of very low energy below the level we know dark. And that might be interpreted as dark matter if you want, is something that interacts very little because they have very low energy. So I call those elementary bits of photons, cycles, non such that which is the model that I have been working lately for gravity. It is published in the last chapter of the book mentioned before by Martin. It's a Lessadian theory. I am trying to revive. I don't think I will have much time to get to cover that.
You got time.
Okay, and you tell me when you want me to stop, and I will stop.
I'll give you.
I can't go for many hours talking.
You're the guest of honor. Just keep talking.
My students used to tell me when I finish my 2-hour lecture and say, Prof, 10 minutes ago, you had to go. You had to go. So I never have to watch.
Yeah, I said an hour and
So
35
just
minutes.
please, just tell me 10 minutes and I will arrange. Okay? So silence is more or less such, and this is a Boston. So this is just a conjecture that might exist, but this is a description of what that matter could be. My idea is that those ions of very small energy, they are photons, of very small energy with the same properties of photons, are the things that fill the whole universe. The whole universe of Patrici is filled with ions of very small energy. Of course, they have to be lower than this, and I have put the limit there. In 1 hertz. 1 hertz down. I don't know where. Doesn't matter for empirical observation. We will find it for empirical observation where it is the limit. I don't know yet. So we decide the upper limit, and so I prove for those ions. And there is something very important that has to do with some of the things that were mentioned yesterday by Anton. I don't see Anton here. Anton Bruman. And by some people else. He was wondering why the photons do not interact in the cosmological model. I also wanted the same, exactly the same. So what I am postulating here is that the field cycles in vacuum, intergalactic vacuum, not here, in intergalactic vacuum, are there where there is the smallest density of matter. They go with speed c in that Patrici space before their first inelastic collision. As I said, I was trained as a nuclear engineer afterwards, and applied nuclear physics. So I know that they do interact, or photons do interact, and they interact through quantum scattering. So before they had the first quantum scattering, they had this C, that is my postulate. By the way, we had never, as far as I know, measured the speed of light far below our solar system, and far beyond our solar system. We only know if measured the sphere, I don't know, perhaps 1 station. That's all. The rest is just assumption. So I am assuming that this is the sphere of science is larger than C0 to be larger than C, our C here, the small C. Okay. Matter, that's the force. So we have space, we have time, we have photons, and we have matter. This is the fourth metaphysical object we have. Matter occupies portions of the Patricius 3D space, as we say. I think that it is continuous, it's obvious. We have holes inside, there's nothing to wonder. And we go down at the Democritus, then we have an atom. But there is a difference. I believe that if we are one way here, we should be all the way down the same way. So this atom has to have structure also. Structure. And it has structure, it can be divided. But how can we have an atom that cannot be divided? That's not the point. So this is because if this atom is divided, it will not be matter any longer. It will be energy. So this thing can be divided into energy. So the basic bits of the atom of matter are two photons or two cycles. And this has been observed, which we know all the time that we can produce in the lab. Their production, when you have a photon, it goes in tools, and when you annihilate an electron and positron, you go back to photons. So the two ways are well known in our labs for applied nuclear physics. They are well known in the 20th century, but they were not known before. So this is something we are using now, our knowledge, to get a better theory of nature using the 20th century knowledge. So, some of the properties of science very quickly. So they move with the C before C naught relative to C to the space sigma inside this Patricius space. After the first energy collision, they have this more cost because they allow some energy. And then they will go on losing energy to interactions, inelastic quantum scattering, and they may be absorbed by matter. And if they are absorbed by matter, they increase matter because of the absorption. And so that might be the explanation, one possible explanation for the increase of mass of the Earth and Earth expansion. If that exists, that's a good explanation. And the regional space with a lot of matter, the average speed of the cycles go down to some value, average, which is more of potency naught. And this means that cycles do not have all, they more exactly the same speed. But if there will be an average, that will be what is called usually the group velocity. It's continental, the group velocity of light. Here. So every region of the universe will have a different average of C, and this is very much in some ideas, some people very, very close to the establishment as my angel. I think it was the last time I saw him in the Imperial College, but I don't know where he is now. But anyway, those ideas have been proposed before. So this is nothing to wonder about, that the speed of light might have different values at different times of the universe or in different regions, because anyway, when you are far away, it's a different time, and we know. And matter, how is matter created? Well, I said, there are everyday processes in the lab per production, electron positron for instance, but in the particular case of two cycles, the two small particles, they have a head-on collision, which had a lot of problems. That was a discussion of several centuries about whether the collision with the particles was hard or soft. They were soft or hard. That was all the philosophers from the Middle Ages up to 19th century, they were discussing this matter. So when you have that, they are not possible to keep Leibniz principle if the two particles are hard. This is why I am assuming that the atom is soft because, and it has a structure, because then we can understand how collisions work. Naturally, we are violating our principles, because one has to be self-consistent. And then, if you have a frontal collision or head-on collision between two cycles, that thing immediately comes to rest. One of the solutions is rest, the other solution is rebound. So if they come to rest, they have to be silenced, and if silence come to rest, they are no longer photons because they are rest. So they are matter. And this is how materialized energy becomes matter for the first time. So you have a region of the universe where there is a frontal collision, there will be a breaking of symmetry, will appear the first atom of matter, and then the next photon that comes to it will be absorbed or will be decreasing the energy in a collision, and that will be the process of all creation and acceleration of matter, and that matter will be increasing velocity, but always, as it is produced by science, that velocity will be lower than the velocity of the photons, because they cannot have larger, because the electrical cannot get more. It's easy to see. I showed that in the problems. And that is consistent with Einstein's idea that the speed of matter is lower than the speed of photons, but for a different reason, completely different reason. So that is consistent with some of the experiments that apparently agree with the special theory of relativity. So, the physical principles of the theory are two: principle of inertial Galileo and the conservation of the momentum. That's the only two principles that I use to derive the whole theory of mechanics. And the two basic principles of Einstein, which are the rules of 20th century physics, are counterpart. Both of them, the principle of equivalence of inertial and gravitational mass, independent of composition, that was Einstein's assumption, is counterpart one, and the principle of the cross-section of the speed of light, as posed by Einstein, is counterpart one. So I don't have very much time to go over those, but I will show a couple of slides just to put you that. Einstein's principle of equivalence, the one, it was revised, the experiment on Olbus, Becker, and Fekete, that was in the 1990s, was revised by these Baham co-workers in 1985, roughly, and they showed that there was a residual. This is, in this column, there is the difference between the mass, inertial mass, and gravitational mass, as obtained by Olbus, Becker, and Fekete. And in this, this is a function of the structure of the atoms. This is the value difference in according to Fishbach, but in my model it is the atomic number, which is closer to chemistry. But anyway, it doesn't matter, it's the same basically here is the same thing. And here, that is, this experiment had two reference materials. One of them was platinum, and the other was copper. Both of them had different cells, different atomic number, and the curve for platinum is different to the curve for copper. And in addition, here is said over here. So in different, the influence of the composition of matter appears in two different senses: down here and up here. So it's clear that the basis.
Can you please explain what the two axes are here?
This is the difference of mass between inertial mass and gravitational passive mass. This one here. And this is a function of composition, of atomic number. Here it is value number, but it's the same because the number of protons in the nucleus is the same as the atomic number. Okay? The same in chemistry. Okay? So this is composition, and this is difference of matter, of mass. So this experiment is very old, but it was interpreted at that time as null, as many others. But here is a very clear influence of composition. So The postulate of Einstein doesn't have any empirical basis, zero empirical basis. And this was why Fischbach co-workers proposed in the 1980s a fifth force. A fifth force. Of course, their model for the fifth force, I don't have it here, but I can say it quickly. The fifth force they proposed was Yukawa type exponential decrease, and that particular model was not sustained by the experiment that were carried out in the 80s and 90s. So they say in 1999, okay, we retire our ideal fish force because the experiment didn't work. But this was still not explained. And so this I explain this now with the science model that I just developed, published in the book 2 years ago. And here it is my calculation. I have here the same delta K, I have here different mass, and I here the same delta K, the delta kappa, calculated with my model. Delta kappa is now calculated directly with the model, which is an atomic model that takes into account cell, the number of electrons around and the structure of the nucleus. That's atomic and nuclear model for gravity. And then I can explain the data with a singularity, directly, with 90% compression. So, given the way the experiment was done in the 19th century, okay? So, this is the evidence for Einstein was not good, but the evidence for the Science model is fairly good. So now it's consistent. Actually, the only parameter I have there was the ratio of the strength of the interaction of the science with the electron and the proton. And I assume, my expectation was that it would be similar to the ratio between the mass of the electron and the proton. And when I made but I left this parameter free to check whether it worked. And actually, when I optimized, I obtained this value. And this value is exactly this ratio. So I was very happy that my intuition was right. Okay? The other experiment, the more the one you mentioned before, that was my small experiment. I made that experiment. I started to talk about this subject in the 1997 or something like that. I revised the whole information about that, and there was always a very small residual in Michelson model experiment, the 187. They only made 36 tenths of the interferometer. It was only three days with 2 sessions, and the interpretation was not resolved because there was some idea from somebody else. But Miller made thousands of tons of interferometer, and we always claimed that the experiment was not moved. That was a small one, but it was not moved. They don't believe Miller, they prefer us. Then these are Michelson Morris data. The 6 experiments they made, 1, 2, 3 at noon and 3 in the evening. I'm not going over those, but you can see that they are different things. Obviously, you cannot go on and average those. Those are different experiments. Obviously, at noon and evening they are different because the teacher are different. I took the line out now. You know here, but they are different on that. And this that go up and go down, it was noted very early by Higgs in 1902 that they were caused by different calibration of the system, of the interferometer. Higgs noted that in 1902 very quickly. And so you cannot go and average this and this, of course not. And then you cannot average this and this because they have different orientations of the Earth relative to the space. So this you can have to analyze them independently and not average. You average them, you obtain 0, of course, clearly. If you average white noise, you get 0. Everybody knows that. So you cannot average this. And you go that with properly, you will get some positive results. I will not go more on that. I will only show you my work. I predicted that say in July you will see something like this blue one, I think, in July of whatever year was that. And I carry out my experiments in July to be on board, and these are very similar to this that I was expecting to see. Up to the I have to correct here to take out the effect of pressure, temperature, humidity, that they were not taken out in my clinical experiments. I did correct for those. Actually, I always corrected for those. And I obtained still a periodical curve that is consistent with what I have proposed. And from that, I calculated the speed of the sun relative to the physical space, and is consistent more or less with whatever other calculations are, legs and so on. So I will not go on that because we do that. Okay. So Einstein's fundamental assumptions are not correct experimentally. The rest is math. I don't care about that. I don't care in the sense I have said. Okay. So conservation of linear momentum is very well known. Everybody knows billiards. These are taken from any mechanics books. You have here the conservation of data in a fluid disk. It's well known. So you can have that from any mechanics books. And what is interesting here, and this is from the PhD book, the old one from the Berkeley series, and you have 2 million volts. You immediately can see here that there is the collision takes some time. So here I was checking that against the ruler here, and you can see that the collision actually takes some time. But you see as immediate collision, actually that is fast. I mean, here there is space. Of course, that space was covered or so down. So it means that the hard balls of billiards are not hard, they are soft. That's consistent with the principle of Leibniz. Okay, wonderful. So this is the process of materialization I mentioned before. You have 2 equal balls that they collide, say in this case they are ions which are soft, and they merge. Then you have this going to 0, so it's matter, and then this is the mass of the soft atom, and that's all. This is the process of materialization when you go from photons into matter. And for the first time, I think, I have proposed a microscopic mechanism for the continuous creation of matter in any modern cosmological model. So this is the first time I have seen this. So this proton collision is very interesting, and that happens in 3-dimensional space. It might be Big Bang cosmology, which I don't believe, but if you believe, it's okay. That makes the change between the radiation-dominated area to the matter-dominated area. So, okay. You can interpret that as Big Bang or not Big Bang. That's up to you. I interpret that. So the 2 fundamental laws of classical mechanics as Cartesian mechanics are conservation of momentum, conservation of total energy. Those 2 are enough to explain, actually, force is not here, force is not a primitive notion, it's a derived notion. So pulling force does not exist in this context, but exists is rather a pushing pressure that appears as you are pressed down as in a sail. You can sail, everyone knows how to sail. Not how to sail, I have seen how boats sail. And then the equations of fluid mechanics are based on conservation of mass and conservation of momentum, linear momentum. And when you put that, those 2, this conservation of mass will be multiplied by C up and down, and you get exactly the same shape as the conservation of linear momentum. And you put these 2 together, you get the 4 equations of Einstein, which are interpreted as representation of space-time. And I prefer to interpret that as a lot of fluid in our space. So basically, Einstein's hydrodynamic equations for gravity are just a variation of the fluid equation. That's all. I said that already in Zacatecas in 1989. This is why and from there, if you have that fluid now, you can derive immediately electromagnetism. If you verify those in the rotational and here and the derivative, then you have with these two recognitions of the fluid here, then you go and immediately obtain Maxwell equations. And for Maxwell equations, you can, or for that fluid directly, you take the derivative as the gradient of P, the pressure which appears in the equation of the fluids, and you get four terms. One the Coulomb, one the Lorentz, and two terms. They are not the same, or might be the same as yours, Charles. One is induced displacement current here, and one new one which is appears in the use where the fluid is compressible, and this is non-zero. So you have here again Maxwell equations appear, and two terms additional coming from the fluid equation. So the fluid equation leads to more physics than the simple Maxwell equation. And of course, as you stressed yesterday, because this fluid equation is consistent with conservation of linear momentum and conservation of energy, which are the basic laws of physics, and that's it. Usually, the violations that people discuss all the time, that whether is conserved linear momentum, and say, well, no, we forgot about the field. But what is the field? Field just is a nickname for the properties of the ether. The ether is there and it has some properties, of course, and that the field is, okay, you call it field if you want, but you have to put it in. Because it carries linear momentum a lot. Okay. So, this is, if you look at the force from the point of view of going down to gravity, it is well known that the forces are the same. In the stationary case, both the gravitational and the electromagnetic one is in every book. And what almost is very unknown is that the gravitational connection that was suspected already by Faraday and by Maxwell, and they have papers on that. I have the copies, I have the copies of both Maxwell and Faraday's conjectures on the connection between electromagnetism and gravitation. Then in 1993, Heaviside sat down and calculated what would be the gravitational field of a point mass in motion. You see a point mass as usual, but you have, as a first approximation is okay. I mean, of course it's okay as a first approximation. And you find here something very similar to what you saw yesterday for electromagnetism. But this is for gravitation. This is a heavy-sized model of gravity, and this is, of course, this term is very similar to what you have seen in Einstein, special theory of relativity. But of course, I'm not relativistic, of course. This was before Einstein. No, it's a couple of details. Actually, it's very sad about this, because Heaviside, apparently he developed this theory much better, and he came into a lot of details, and he had it ready for publication in 1925. And you know what? Borrowers came in to his house, I don't know who sent them, the girls, and they took everything away, and this is paper, so he was very sad. I didn't recover from that. Very sad. Anyway, but here I have put that in a paper, at least up to this stage. in addition. Okay? So, so the connection between gravity and electromagnetism is there already. So we don't need to verify anything else. It's already from mechanics. You have a fluid. From the fluid, you have electromagnetism, and electromagnetism is the same as gravity. So everything is done. So here also I want to mention to comment some a little bit on something that was mentioned yesterday by Charles also, that has been bothering me for 20 years now, which is the question of whether there are longitudinal solutions of the way of Maxwell equations. There is a person called Evans, Myron Evans. I don't agree with everything he says, but he is right in saying that in Maxwell equations there are longitudinal solutions that are consistent with Maxwell equations, which is contrary to the majority view. And I showed with my friend Guzman, because a colleague of mine in physics there in Colombia, there are solutions, mathematical solutions that are consistent with Maxwell equations. And then at that time I also manipulated Maxwell equations because I was concerned about Dirac's idea that why there isn't a monopole. Why there isn't a monopole and whatsoever, there is a term missing in the Maxwell equations. Well, I found something very simple. I just made this little manipulation, this one here. I just redefine a P plus and a negative 1 field as this addition, elementary arithmetic, vector arithmetic. And I did that, and here, surprisingly, you can see that the equations that were before asymmetric in the sources, they are now symmetric in the sources. You can see here they are symmetric in the sources, both in the J source and in the rho source, the charge source. Amazing. No need for more poles. What? By the way, I don't think Maxwell equation is the only way of doing it. I mean, there were also many other competitors at that time. There was Bell, there was Neumann, there was Gauss. I mean, there are many other alternatives. But I'm talking about Maxwell because it was known, but anyway. So he's here. So when you do this, it is already published in 1997, it's getting the reference in one of his letters. When you do that, I can, of course, derive as usual the whole equation for this. I mean, I can put that in terms of gravity, vector equation as usual, and I can focus the fields, blah blah blah. That's something normality source, blah blah blah. All that. You can manipulate that and find out the nice symmetric well equations. And then when I interpret that in the context of the dipole, now I go to Hertz, who was the Almar Hertz, he proposed the dipole, and my idea of the photon is in the direction of the dipole, charge dipole, and so surprised. One of my students just made a calculation for my model P and N, the one I showed you, and you can see how they look. They are looking very nice helical fields, longitudinal fields, helical fields, going out. Wonderful. This is she made this calculation in 205 also in M master thesis, and these are the helical fields associated with my PN, which are the same as Maxwell's, because I didn't do anything, I didn't put any physics in there, I didn't put math. No. So it's exactly the same physics the Maxwell equation is in the PN field. Exactly the same physics. Don't do more. And of course, those things are this that you also like to zero. These are the helical fields are there. These are my photo for my collections. These are the helical fields that are in nature a lot. But then, unsurprisingly, about 1 day before I came here, the 3rd of November, in the TV in Colombia, I took that from my TV screen. There was a National Geographic program, and they were showing this wonderful helical fountain that was observed about 8 years ago in Tromsø. It was observed in Finland and in Tromsø in Norway, and apparently also in Russia. And this is a very nice, very large helical field also associated with or similar to Aurora Borealis. So, those are connected more likely to the neutrino fields of the being time. And surprisingly, also by that time, I obtained new solutions for the scalar wave equation for the but of course, as the vector has the mole as components, they are also applicable there. So you have published in Foundation of Physics Letters in 1997. They are very interesting non-periodic solutions that behave as solitons. They have those in time, so they look very much like the helical thing, but they are new. They are not the same as planar standard one that you should find for the wave equation. They are non-periodic solutions for this. Non-periodic, and they have longitudinal components. Very strong ones. You are invited to see them. I have the detailed analysis of that is in the paper in Spanish, unfortunately, in the Journal of University, National University. But if someone is interested, I can send you the Spanish one, which is longer than this particular one. Has more details. So, I don't think I have more time now. Then, research. So this finishes the part I have in my work in electromagnetism. And what about our gravitation? Research mechanism became to explain what Newton left open. That's when he said, I don't make any hypothesis no finger. So when he was asked what was the mechanism for the propagation of gravity, he didn't want to take any stance. But one of his students, Fazio, or disciples Fazio, and then 100 years later, he proposed that there was a shadowing mechanism in the ether of the particles that he used to call them ultramundane particles research, that are called ions. So if the ions are here, then if there is a body, there will be an attenuation of the ions or the photons in this direction, and somebody here then will be attenuated by this. The photons coming in this cone will be attenuated, if they're here, and if they're here, the photons coming in this cone will be attenuated. So this explains why there is a variation in R2, 1R squared. And when you develop that idea, as I said, you can go and obtain the data I already showed you. But I only want to show you the equations. The equations are, this is the Newtonian equation where you have the R2 dependence, but then you have here an exponential correction, which may account for some decrease a long distance from the body. And here also, the same way as Charles did, I also obtained G from first principles as a function of the geometry and the composition of the bodies. Here is G obtained as from first principle, and KP is also part of that where you are observing that. And you have a new term in the design force. In addition to the imperial term, there is another term that does not depend on the product of M1 and M2, but only depends on the observer, and this is interaction with the vacuum. So this is a term that has to do with the vacuum. So there is a prediction clearly here that can stand falsification. that can be observed and will be differential here. And when you have a different non-spherical geometry, which is also very important for the foreign situations, if you have, say, a flat geometry, which might be the situation where you have a spiral galaxy which is almost flat, and that scale, it's almost flat, you can look it from here or from here, it doesn't matter, it will be flat. Then you have a different situation, and the two terms of the equation are these. This term is exponential one, and when you expand this, because this is very small, you take this, and this term here is the explanation for a flat rate of galaxies. The velocity of the flat velocity of galaxies is here. This term is constant, and there is a small correction that goes down a little bit as observed in the current exploration of what is called MOND, the Milgrom's modified Newtonian dynamics, which I don't like it because there is in the end there is a little violation of linear momentum there, but not in the fluid itself. When you do that from the fluid, you don't have a violation. So here you have it, the equation that explains the flat rate velocity of galaxies. Exactly the same equation. And there is another one, interaction also with here, with the interaction with the vacuum, same with the sinus, with the vacuum, with the dark matter, whatever you want to call it. So this is this. So this is also published in my book, in the 2 or 3, the one that Martin helped us a lot with the English, because of course we don't speak English. And this is what Einstein said regarding Michael experiment, or Miller's experiment rather. The system of non-trivial positive effect will affect deeply the fundaments of theoretical physics as it presently accepted. So he was talking about Miller's work, and okay, he said, so I have revised it, and there is now for your attention. Stop here.
Time for a few quick questions. We could use a few extra chairs, yes.
I'll bring some extra chairs. I just got a call that y'all wanted extra chairs.
I have one comment.
Go ahead.
If you look at the unification of fields in terms of the interaction, I look at the thing as actually the more simple thing is the unification of all the forces is that there's no one particle has only one interaction. All the existing particles have many interactions instead of just one. For instance, an electron has a mass, is a charge, and go through interaction, etc. So unification exists in terms of the elementary particles.
Well, elementary particles
20 minutes because
it's just those particles that appear as different in just a matter of scale.
Actually, it was all
a particle is a soliton, the fluid. So that soliton may have, according to the shape of the soliton, we have different interactions. It's not the same when you interact with a round thing or a cube. You will find differences there. So it matters of the solid. So look, I know that I do. But it's a matter of the structure, and that is a relation of many components.
Can't get it.